Okay, let's start. So maybe first, okay, so turn on video. And first we discuss the exercise that we last time discussed. Okay, so let me share the screen first. Okay, so I think I have some trouble. Sorry, I think I have some trouble in Zoom today. Just a moment again. Probably you're still not seeing the screen. This once again. Okay, I think you are now seeing the screen. So last time that we discussed this exercise 1, now exercise 6, problem 1. So the weight of 6 newborn babies are given. So these are 3.8, 4.1, 2.9, 4.4, 3.3, 3.6. And assume these follow the IID. And the test if population mean of newborn babies is significantly different from 4.0. So at first that we consider Okay, so at first we consider these 6 observations. So okay, so we define these 6 numbers as a vector. So let's say this as x. Now we define x, and we want to test this. And we are assuming this has normal distribution, so we can do t-test. So we can do this t-test, but if you just put the x here, then this basically tests if mean is 0. That does not make any sense because these numbers are weight of newborn babies. So of course, these are larger than 0. So we want to set the alternative hypothesis as the mu is equal to 4. So we have to put in this way. So test if population mean is significantly different from mu. So now the null hypothesis is this. So we can get this test result. So p-value is 0.2117. So actually it is not different from 0. So our x bar is not significantly different from 0 because the p-value is 0.21, that is larger than 0.05. So at 5% significance level, that we can say that it's not significantly different from 0. Okay, so now that we go to question 2, the calculate the 95 confidence interval for mu. Actually, this is already given here. So 95 confidence interval is 3.1 to 4.2, 4.25. So if we want to change the 95% into different number, for example, 99% confidence interval, that we can, the confidence level, conf level. Then we can get the 99% confidence interval, which is a little wider, 2.79 to 4.58. So, but the 95% confidence interval already here. So 3.11 to 4.25. And the next one, suppose we know the population mean weight of newborn babies is 4.0 kilogram, and the distribution of weight is normal. We have 1,000 simulated sample of 6 babies in the, so basically, the another file includes the 1,000 samples. Each sample includes 6 babies. And we want to calculate confidence interval for each sample. And we want to see how many confidence intervals include the true mu. Okay, so I think that my folder here, my directly includes the newborn .csv file. So we want to access to this. So at first we have to set the working directly. Okay, so at first it's a good idea to get the working directly. Then we set working directly as we want. So this is my default, the working directly. So we put this pass, the teach. And in this way, exercise 6. Then now we want to load the data set, the newborn CSV. And I think that this file is separated by space. I think that this is the raw data, and it maybe tab or space, maybe space. So it's separated by space. So, and it does not have header. It's just first line is just the first observation. So header is false. Header false is actually default, so you don't really have to specify. And the separation symbol is space. And in this way, I think that, yeah, so these variables are loaded. So we want to get the confidence interval. So if we got maybe, okay, so head of the, if we use the first line, then we can generate one confidence interval, and the second line, another confidence interval. So basically, this is the first row. So if we do this, then we can calculate confidence interval. And actually, we know that the true mean is 4. So 4 is included in this interval. So 3.19 to 5.05. So this is interval, and it includes 4. So in this first interval, it includes 4. And the second interval, again, it includes 4. So this is 3.12 to 4.48. So I think the most of the time it includes 4. Yeah, but maybe this one, just barely includes 4. So 3.06 to 4.037, so 4. But you can imagine that if we try everything from the first row to 1,000th row, maybe some of them, some of them does not include 4. So we want to see how many of these that includes 4. And at first, before calculating it, we can guess that about 950 confidence intervals include 4, and the other 50 do not include 4. Maybe 955 confidence intervals includes 4, or maybe only 940 intervals includes 4. But about 95% of 1,000 confidence intervals include 4. So we can count this. Maybe we have to use the for loop for this. Yeah. Confidence interval that you can check how this test result is constructed. So you can check the structure of the first test result. And confidence interval is saved as the $, the conf.int. So actually, if you type t.test d1 and conf int, then you can get this number and this number. To access to this 3.19, maybe we have to, do this and this. So actually this is the lower bound and this is the upper bound of the confidence interval. So we want to see if this includes 4 or not. Yeah, you can do it in one line, but maybe it's easier to write a code in another text editor. Sorry, it cannot be larger. So we have the lower bound and the upper bound. So lower and upper. And we want to see if the 4 is included in this. So that means the lower bound is smaller than 4 and the upper bound is larger than 4. So we want to see if this is true. So if you run these 3 lines, then we can see if the 4 is included. In this case, the 4 is included, so it's true. So we want to count how many times this happens. So now we have to generalize this into ith row of the data. So we have 1,000 observations, so that we have the 1,000. So maybe each time that we make a vector, so maybe we prepare the numeric vector of 1,000 element as maybe Ci, and we want to define the value of Ci as true if it's included, the 4 is included in the confidence interval, and if not, false. So for example, I is equal to 1. So these 3 lines, maybe we have to define Ci, and the Ci is just the empty vector. But if you plug in these 3 lines, then we can get the first number is 1. 1 is true, so 1 is true, and the 0 is false. So we want to do this for I is equal to 1 to 1,000. So we have to do this. Then you can see maybe head of Ci, maybe the first 40 observations we see. And we can see most of the time it includes 4, but the 1, 2, 3, 3 of the 40 times, the confidence interval, 95% confidence interval, the misses the 4. So we want to count how many times. So this is just a summation of Ci. So we can get this is the answer. So this is 952. So about 95% of confidence intervals includes 4. So in this simulation, we can clearly see the meaning of 95% confidence interval. If we have many samples, then 95% of the samples includes the true parameter. So 95 confidence interval is the algorithm to achieve that situation. Any questions so far? Okay, and the next question. And test H0 against H1. Okay, H0 is mu is equal to 4. H0 is mu is not equal to H1. Mu is not equal to 4.0. And we want to calculate p-value. How many times H0 is rejected at the 5% the significance level? How many p-values are less than 0.01, less than 0.05, and less than 0.10? So p-value always has uniform distribution between 0 and 1. So p-value, so the p-value, so the p-value is the probability that more extreme event happens than our sample. But our sample, if we randomly pick up a sample, then that is just random result. So the probability that more extreme event happens is between 0 and 1, and the uniformly distributed. So p-value has uniform distribution. So that means 1% of p-values should be less than 0.01. 5% of p-values is less than 0.05, and 10% of p-values should be less than 0.1. So yeah, we can check it, and we can use the same code for this. We have seen that the t.test output has this structure, and the p-value is calculated in this, saved in this place. So $ p-value. So if we use this p-value, then we can get the whether or not that this is less than 0.1 or 0.05 and so on. So we want to save these p-values. So maybe we have to define another vector, the PV. This is the vector to store 1000 p-values. And then we want to, each time, in case of PV, we want to define this, and PV is just the vector of 1000 numbers, zeros. And we want to store the p-value in PV. So maybe this is once more, we have to run this for loop once again. But we can test the p-value of the t-test for ith line, that is the p-dot value. So in this way, we can save all p-values. So we can do this again. Then we can see head of p-value, maybe first 20, we can see this. Maybe it's a little bit hard to see, so maybe we just round this into just 4 digits. Then, oh, this is strange. Oh, sorry. Test if. Yeah, so yeah, actually this is the actual observation. So the sum of them include p-value. Yeah, it sounds strange. Sorry. Maybe we can get the test result first. So the first test that we can get the p-value of this. Oh, I think, sorry about that. So the null hypothesis is set at mu is equal to 0. So we have to set this as 4. So confidence interval is not affected by null hypothesis, but the p-value depends on null hypothesis. So we have to modify the code. So we have to do the t-test, but not just t-test, but the t-test with mu is equal to 4. Then we can calculate the p-values. Maybe just we reset p-value again and the substitute p-values. Then so first 20 p-values are here. And these p-values ranges from 0 to 1. Of course, p-value is a probability. And actually, this is almost evenly distributed between 0 and 1. You can get the histogram of p-value. You can see that this is distributed almost uniformly between 0 and 1. So of course, we only have 1000. So we have some difference between the height of these bins, but mostly this is uniformly distributed between 0 and 1. And you can see that the how many p-values are less than 1 at 0.1 by doing this. How many p-values are less than 0.1? Then this is about 10%. So 93 over 1000 is about 10%. How many p-values are less than 0.05? 48. So 48 is about 5% of the entire number of samples. And 0.01, maybe this is just 10, so maybe we have some discrepancy, but yeah, 12, so 12 over 1000. Still, it's close to 0.01. So this means the p-value is calculated correctly. So if null hypothesis is correct, then so the t-statistic follows some distribution, but the p-value is calculated correctly so that the these property holds. The only 5% of observations, 5% of samples achieve the p-value of less than 5%. So if we use 0.05 as the threshold, then basically we only made 5% error to reject H0. Even if H0 is true, then we have 5% risk to reject null hypothesis. So this is D. Any questions? I think maybe I think they're all breakout rooms only did the question 1, maybe question 2. But just we stop here and then we start the chapter 5. Okay, so I will screenshot the attendees. Okay. Okay, so now we go to chapter 5. So let me see. I will share the slide. Do you have any questions so far about chapter 5 or any quizzes? Okay, so today that we will cover the chapter 5, the last section, and I mean 5.6, and also we enter chapter 6. Chapter 6 is pretty important chapter, so just make sure that you catch up with the materials. Okay, so the last week we discussed the one sample test and the two sample tests. So one sample test, in one sample test, we have one sample and we will see if the true mean is equal to something or different from something. So for example, we can check if we can test if the population mean of blood pressure is 120 millimeter Hg or not 120 based on one sample. One sample means a set of observations from the same population. And the two sample tests, we have the two samples, and our objective is to compare the population mean of the two groups. Okay. For example, the blood pressure for treatment group and the blood pressure for control group. And here that we discuss the paired test. So basically we have two samples, but the two samples that corresponds each other. So the situation is like this. So we have the group A and group B, and so maybe we start with, so these two samples are from the same experimental units. So if the two samples are two variables from the same experimental units, the two variables are often the dependent. So we have one-to-one correspondence between the two variables. I mean, the two set of observations. So therefore, it is more appropriate to take the difference between two variables and then do a one sample t-test. Okay, so the situation is like this. So we have the 5 cars, and the maybe tire A is maybe the left front tire, and tire B is right front tire. So these are almost under the same condition. So the same automobile, so the weight of the car is the same for these two groups, and the condition the car runs is the same, car drives is the same as well. So as a result, you can see that these numbers are similar within each car. So 10.6 and 10.2 are similar numbers, 12.3 and 11.8 is also a similar number, and 9.7 and 9.1 are similar numbers. So we have one-to-one correspondence, and we have similar numbers. So in this case, certainly it's not appropriate to assume the tire A and tire B are independent. So two-sample test is not really appropriate way to test the difference between tire A and tire B. So tire A and tire B are the wear of two types of wear of two tires. Oh, sorry. In this example, the wear of the two types of tires, not the left front and right front, but the yeah, maybe suppose that we have different tires on the left front and right front. So conditions are similar, so that these observations are highly dependent. So in this case, it's more appropriate to take the difference between these two numbers. Then we get 0.4, 0.4, 0.5, 0.6, and 0.5. And in this case, we can see that the tire A's wear is consistently more than tire B. So we can do actually the one sample t-test on these 5 observations. So basically, we calculate the average. This is the mean of difference. And standard deviation of these 5 observations. Then we can do the one sample t-test. So that is called the paired t-test. So paired t-test is basically the one sample t-test. So even though the original observations are for two groups, the tire A and tire B, but it is more appropriate to take the difference than do one sample t-test. So that is the paired t-test. So the important thing is the variable A and variable B. Two variables are on the same sample unit. So in that case, we do the paired t-test. So in the past, some students asked me when we have to do two sample t-tests and when we have to do paired t-test. So is it true that the sample sizes are the same? We should do the paired t-test? But actually not. So even if n is equal to 100 and m is equal to 100 and we have two groups, still these two groups may be just independent. Maybe we are comparing the test scores for 100 students in the United States and the 100 students in Germany. So those 100 observations, those two groups of 100 observations are entirely independent. In such a case, we do two sample t-test. But like in this case, we have the two variables, but these are on the same experimental unit. So in this case, we compare. So we take the difference first, then do one sample t-test. So that is the paired t-test. So maybe even this example of 100 students in US and 100 students in Germany, if these are 100 twins, one of the twins live in the United States and the other live in Germany, then maybe we can do the paired t-test because each pair come from the same family. But so the point is whether or not these two groups are measured on the same experimental units. Yeah, and actually, you can imagine that this difference, D, is significantly different from 0. You can see that if we take the difference between A and B and do t-test, the p-value is very small. That is pretty natural because we have, I think, the 0.5, 0.5, 0.4, 0.4, 0.6 or something. So it's consistently positive. So we can say that the wear of tire A is more than wear of tire B. Yeah, and this can be also done by t dot test the two vectors A and B, and paired is equal to true. Then we make the same result. Maybe some explanations are different, but basically this does the same test. And actually, I don't have it here, but if we do two sample t-tests here, probably we cannot detect the difference, because for tire A, the average is 10.24, and tire B average is 9.76. So difference is 0.48. So that is actually the same. But the standard deviation, these standard deviations are much larger than this 0.083. So we have large variation between experimental units, the cars 1 to 5. So this is actually 1.3, and this is also 1.3, about 1.3. So difference is only 0.48. If standard deviation is 1.3 for each sample, we can imagine that we cannot reject null hypothesis. So actually, not only the two sample t-test is not appropriate to do, but also this often fails to reject null hypothesis. Yeah, so mathematically it's nothing. So it's the same as one sample t-test, but practically two samples on the same experimental unit is different from two independent samples. Any questions?
Professor, I have a question.
Yeah, sure.
So could B minus A be done as well, or is it just strictly A minus B?
Sorry. Once again, sorry.
Could B minus A be done,
Oh
or
yeah,
is it
B
strictly
minus A is fine. Yeah, B minus A and A minus B, both ways are fine. Yeah.
Okay.
Yeah. Sometimes the alternative hypothesis is one-sided. So, we have to be careful about the direction of the test, but B minus A, A minus B, either is fine. Yeah, and if the two samples are paired, but we cannot apply the t-test because the violation of normality, then we can use the Wilcoxon-Signed-Rank test. We don't do any detail here. So that is paired test. Okay. Any other questions? Oh, I think I got the question in chat. Why is the paired t-test inappropriate for independent experimental samples? I see. That's a good question. So the question is, the other way. So suppose that the two samples are independent, and what happens if we do the one sample t-test? Actually, the result is approximately the same. Yeah, approximately the same. Yeah, that's the simple answer. But the two sample t-tests have some advantage over the paired t-test if two samples are independent. For example, we can assume different standard deviation for each population. So yeah, maybe that's the reason. And also that the paired t-test can be applied only if the two samples have the same sample size. So that is another reason. Yeah, that's a good question. So if two independent samples and the sample sizes are the same, the variances are the same, and the variances may not have to be the same. Okay, so two samples have the same sample size but independent. What if we do paired t-test? Basically, we get mostly the same result. Yeah, maybe slightly different because of the slightly different assumptions in the tests, but basically we got almost the same result. Yeah, but two independent samples, often we have a different sample size. So anyway, we cannot apply paired t-test. Okay, so that's it. And we have to go to chapter 6. The chapter 6 slides are available. So you can download it. And chapter 6 is about the regression and correlation. I hope that you have already studied it in 20 to 10, maybe just 1 or 2 weeks. And chapter 6 and chapter 11 are related. And chapter 6, that we explain some variable by just one variable, another variable. So we explain y by x. And chapter 11, we explain y by multiple factors, like the multiple variables, x1, x2, x3, and so on. And these two chapters are roughly equivalent to chapters 2 and 3 in the reference, the practical regression and ANOVA using R. So if you need more explanation on the concepts, then you can refer this book. So this book is available on the Comprehensive R Archive Network, so you can download it for free. But we just review everything from scratch. So simple linear regression. So at first, we have two variables. And when we assume that the variable y depends on variable x, we say x as independent variable or predictor and y as dependent variable or response. Some other names are also possible. Sometimes the people say x variable are covariate. And y is, usually just the dependent or response variable, maybe x, maybe predictor variable. So those are the names. Yeah, and examples. The one example is x is total calorie intake of a mouse and y is the weight of the mouse. So more calorie intake they have, then more weight increase. So we can probably explain x. We can explain y by x. And next one is the finance example. X is interest rate this year and y is inflation rate next year. So usually once the Federal Reserve tighten the financial market, then it affects in the long run, maybe for the next year. So interest rate gets higher, then next year inflation rate goes down. And another example, x is the horsepower of a car and the y is the maximum speed of the car. This is also positively related. So we can explain y by x. Maybe the second example is a little different because the x gets higher, y gets lower. The first example and the third example, x gets higher, then y gets higher. Yeah, and this isn't really the causation, but just correlation. So horsepower of a car is higher, then maximum speed of the car is higher. It sounds like it's causation, but you can just flip the relationship as well. So maximum speed of the car is higher, then the horsepower is higher. Usually maximum speed is easier to observe. So if we just flip x and y, it makes sense. And again, this is not causation, but just the correlation, so not causation. So it is even possible to flip the relationship between x and y in the second example. Inflation rate next year is higher, then that implies the interest rate in the previous year is, the inflation rate next year is lower, then it indicates that the inflation rate this year is higher. So this is just correlation, so not causation. So even the time point, the time. So we go back the time, and still it's possible that we can explain the y by x. We don't really assume that the x happens first and y happens later. Maybe just the different, the other way around is also possible. So just not causation, just correlation. So basically, any statistical models cannot explain causation. So causation can be proved only by experiments. So that we randomize two groups, that we make two groups, that we give some prescription to one group, and that don't give prescription to the other group. Then we compare. Then we can test. We can check if there is causation from the prescription to the maybe blood pressure. But without experiments, basically we don't have any way to check causation. Of course, statisticians think about a kind of approximate method to show causation. So, but basically, fundamentally, the statistics cannot prove the causation. So just correlation. Even if we say predict or some response, it sounds like it's causation, but always this is just correlation. Yeah. And we usually use the lowercase x and y, at least for this textbook, because we want to reserve capital letters for the matrix representation, which we will discuss it later. And simple linear regression, we assume that we observe data from x1, y1 to xn, yn. N is sample size. So just a fixed number. And the linear regression assumes that the y sub I is equal to a plus b times x sub I plus epsilon I. So x may be the calorie intake and y is the weight gain, the weight of the mass, then the xi explains yi. So x and y are observed, and a and b are called parameters. So a kind of the true relationship between x and y. And epsilon I is called an error. So, some other factors come in, maybe some genetic reasons or the temperature of the cage, or maybe other environment factors, that those affects the weight as well. So we have some noise, epsilon I. So that is our assumption in linear regression. And this is called simple linear regression or univariate linear regression. Yeah, so in this model, A and B are constant, but we cannot observe it. And X is a deterministic. Yeah, so we consider the calorie intake of the mouse as deterministic. It's also possible that X is random, but at least in this course and classic statistics assume that X is deterministic. And epsilon is random because this is error. So error is random. So epsilon is random. And you can see that the A is constant and B and X, B is constant and X is deterministic. So these are deterministic. So epsilon I is random. So yi is also random. So y and epsilon are random. And x and y are observed. So that is the structure of this probabilistic structure of this model. And our objective is to estimate these A and B. And sometimes additional assumptions such as epsilon sub t is independent and identically distributed, we say IID. And also we assume that epsilon t follows some normal distribution. So normal distribution with zero mean and the variance sigma square. Sigma is actually another unknown quantity. So this kind of assumption is usually assumed, and actually it is possible to estimate A and B without these assumptions, but these assumptions are needed for the sum of the statistical results, such as testing on A and B. So we can estimate, for example, A and B, like A is 3.1, B is 4.5. But if we want to test A is equal to 0 or something, then we need this kind of normality and IID assumptions. Yeah, so now how to estimate this A and B. So we have variable X and variable Y, and we have observations, 1, 2, 3, 4, 5, and how to determine this line. Actually, this line is determined so that these size, the sum of square of these errors is minimized. So that is our criterion to determine this line. So if we, for example, shift the line a little bit, sorry, like this, then, or maybe more interesting example, maybe this. Then you can see the sum of the squared errors, the sum of epsilon I squares gets larger. Actually, for epsilon 1, epsilon 3, epsilon 5, the error size gets smaller, but the epsilon 2 and the epsilon 4 gets much larger. So that makes the sum of squared errors larger. So actually, with this rule, if we determine the straight line with this rule, actually it's optimal in some sense. Also, we can define, for example, this kind of line, but in this case, the error size for fifth observation is very large. Also, first observation, very large. Maybe third observation and the fourth observation, somewhat good, but this is not actually the good idea. So actually, this is the optimal line. And epsilon I is equal to the yi minus parenthesis a plus b times xi. So remember that the yi is equal to a plus b times xi plus epsilon I. So we can express epsilon I as this. So basically, this is a function of a and b. We can say this is some function of a and b. So yeah, we can find the pair a hat b hat to minimize this function. So in this way, we can determine this fitted line. And how to calculate a hat and b hat? How to minimize the sum of squared errors? And this is the answer. So b hat is at first calculated by this. So denominator is a kind of similar to variance formula. Yeah, if actually we put 1 over n minus 1, then it becomes variance. And this is covariance of xi and yi. So it's a kind of a reasonable formula. So b hat. And how to determine a hat? A hat is intercept. So actually the a hat is determined so that the x bar, y bar is on y is equal to a plus bx. So a plus bx is a kind of the trend line of the observations. So it's natural to assume that the the center of the data, x bar and y bar, is on this trend line. And actually, this is true mathematically. So once you get the b hat, we can calculate a hat in this way. So later we discuss more convenient formula, but this is the formula for at least simple linear regression. I got a question. Is the result you get for A and B the same if you use the sum of least force powers? No. This really depends on the situation, and we have some theory for different function than this. But if we change this as 4 or often, we take the absolute value of this, just not squared. So that is another regression model. But this square is good in several ways. at first, the sum of squares is a very natural quantity. If we think about the distance between point A and point B, and if A is x1, y1, and the B is x2, y2, then the distance is, the square root of x1 minus x2 square plus y1 minus y2 square. So the kind of natural quantity, the sum of squares is natural quantity. And computationally, it's very convenient as well, because we want to maximize this quantity, right? So maximize this quantity. So, this is basically quadratic function of A and B. The quadratic function, typically, it's the parabola. This is very easy to maximize. So we have just one, the global minimum, and it's also easy to apply some approximation methods, such as Newton method, and so on. What happens if this makes 4? Then actually basically the largest error has a lot of influence on the entire summation. So basically, if we make this into 4, what happens? Actually, some extreme observations that determine the straight line. Yeah, that may be good in some cases, but in most cases, the 2 is pretty reasonable in terms of estimation easiness and also the mathematical justification. And also, actually, we can prove that this estimation is MLE, maximum likelihood estimator, under normality assumptions. Yeah, that's a good question. Yeah, 4 is actually the not very popular case, but the absolute value of yi minus a plus bxi. So this is often used, and this is called quantile regression. And the benefit is the extreme values that do not affect the estimation much. So if we have recording errors in the data, that probably using absolute value makes estimation more robust. Yeah, and you don't really have to memorize this formula, but you can see this. Yeah, the first formula also has some interpretation. For example, what if all y values becomes 100 times larger? So what if this becomes 100 yi minus 100 y bar? Then actually the b hat becomes 100 times larger. This is very reasonable, because y becomes 100 times larger. That means just the unit has been changed. For example, if the unit for y becomes from meter to centimeter, so this becomes 100y. So in such a case, the slope also has to be 100 times larger, right? Because the unit has been changed. And actually, that is true for this formula. And the unit for x, basically we can say the same thing. The slightly complicated because the x is in both denominator and numerator, but you can prove that as well. I mean, the other way around. So if x becomes 100 times larger, then the y, b hat becomes 100 times smaller. So we have to multiply 1 over 100 for b hat. Yeah. And this is one example. Maybe this is not really the optimal statistical analysis, but this is condominium price data, and the x is square footage of condominium, and the y is price of condominium. We want to explain price by square footage. So this is actually done by the cities to impose the property tax. So basically, we have to determine appropriate price for each condominium. So we calculate the square footage and we estimate the price. So that kind of thing is done by each municipality. And okay, so we have some positive relationship. we have, if the condominium have larger square footage, then price is higher. Yeah, I think this is from 2009 or 2010 data. We only picked up condominiums because the Detroit have many houses whose price is $1 or $1,000. But condominium is maintained by the association. So usually we have more, stable relationship between square footage and price. And this can be done by this code in R. So this is data, and suppose data is this. So data frame have two so two variables, and actually we attach the data set. So the price and the square footage are now used as global variables. And we put the LM. LM is the code for linear regression. And then price, the tilde, and the square footage. Then we can run LM model. Then we can get this result. So intercept A hat is negative 265, and the B hat is the 0.2473. Yeah, we will see more detailed result later, but at least to get A hat and B hat, this is sufficient. Actually, this symbol is a little tricky. So at least on Mac, we have two symbols, the one tilde and maybe larger tilde. And we have to use this larger tilde. But once we copy and paste onto the text file or Word file, actually this becomes small tilde. So if you cut and paste this, probably you got an error. So you have to replace this tilde by this another font of tilde, another maybe, yeah, not font, another tilde. So it's confusing. Yeah, so that is the tilde is upper left of the keyboard. So shift plus upper left key. Yeah, so this is numeric result. And how to make this plot? Actually, this plot has this straight line already. And this can be done by this. So plot square footage and price. This is just scatter plot. And we overlay this AB line. So AB line is y is equal to a plus bx. So we have to specify actually a and b. But once you put this linear regression result, it automatically extracts this a and b. So you can also put AB line negative 265.025 and the 0.2473, then we can get the same result. I got another question. What does the tilde operation do by itself? This tilde basically means that the left-hand side is explained by right-hand side. So that symbol is usually represented by tilde. So even the not code, but just usual statistical sentence, when we say y tilde x1 plus x2, that means y is explained by x1 and x2. Sometimes tilde is a little bit vague, not really y is approximately equal to x1 and x2, but the y is explained by x1 and x2, possibly maybe 1 plus 2 times x1 plus 3 times x2 plus some error or something like that. So this symbol means the left-hand side explains right-hand side. Another question. So can we do anything with the tilde operation in our own code? What do you mean? Can we do anything with the tilde operation? Like, can we? Oh, okay. So, can we use it in our own functions that we made? Yes. Oh, I see. So tilde is just reserved for regression models. And in your own code, that you can use tilde. For example, that you define functions. I'm not exactly sure, but yeah. So yeah, it's possible that in a function of x, y, or something, then you can use the lm y tilde x, and we save this result, and we extract first object of this, or something like that. That is possible. Yeah. So tilde is specific, kind of grammar to define regression model. Yeah. Yeah, and the residuals. So remember that the y is equal to a plus bx plus epsilon. Sorry, I got another question. So I mean, when I try to run the code, the x tilde y for two vectors, I can't seem to figure out how to extract any useful information from that object. Yeah, so I think the tilde is always used in a regression model. So the a kind of LM parenthesis y tilde x parenthesis is just one set of code. So if you just type y tilde x, then R can only recognize the model. So basically R cannot do any calculation. So yeah, so in maybe to be more specific, actually the price tilde square foot. So this kind of phrase, this determines the model, and that we estimate this model by this LM function. So if you just type y tilde x in your R session, then basically R only recognize the model, but do nothing. And yeah, so that's the fact. Okay, so remember that y is equal to a plus bx plus epsilon, and the y and x are observed, but the other quantities are not observed. And but once we estimated a and b, actually the epsilon is calculated by y minus a minus bx, to be exact. So more precisely, y minus a hat plus b hat times x. So a hat and b hat are just estimates for a and b. So that we can approximate epsilon by this quantity. So we say this as epsilon hat. And this is called a residual. So epsilon is an error, and epsilon hat is called residual. And residuals are used to check model assumptions on epsilon. So we often assume epsilon are IID and the normal 0 sigma square. And we can check this IID assumption and normal assumption by using epsilon hat. So actually, epsilon and epsilon hat are different quantities. So we cannot exactly check epsilon, but often we just see those two quantities are almost the same. So we check epsilon hat to see the assumptions of epsilon. Do you have any questions? And the next one is matrix representation. So we have n observations in this simple linear regression. So we have basically n equations. Y1 is equal to a plus b times x1 plus epsilon 1. Y2 is equal to a plus b times x2 plus epsilon 2, and so on, up to yn is equal to a plus b times xn plus epsilon n. So it's pretty natural that to use matrix representation to make it simpler. And we want to write this as y is equal to x beta plus epsilon. Here, y is a vector of y1 to yn, and X is a matrix of vector of ones and the vector of X, X1 to Xn. And the beta is A, B, the vector of two element A, B, and epsilon is a vector of epsilon 1 to epsilon n. So in this way, the the y is equal to x beta plus epsilon. So you can see the product of x and beta is, you can see 1 times a plus x1 times b. So that is the a plus b times x1. So we can write in this way. And with this way, we can estimate a hat, b hat. A hat, b hat is represented by beta hat. Beta hat is calculated by just this matrix product. You can see X is n by 2 matrix, right? So X transpose is 2 by n. And this is n by 2. So entirely, this entire quantity is 2 by 2. So we can take the inverse. So still this is 2 by 2. X transpose is 2 by n because it's transposed X, and Y is n by 1 vector. So the product is 2 by 1. So entire quantity is 2 by 1. So actually we got the 2 by 1 quantity, and the first element is A hat, and the second element is B hat. And this is very important formula. So usually the statisticians memorize this one. And this is much simple, especially that when regression model has more parameters, more predictors, then this form is much more convenient, practically and also theoretically. X transpose is a transpose of X. So X prime is the transpose of X. Yeah. Do you have any questions so far? And how to prove this? Actually, this proof is probably simpler than the previous, the formula for A hat and B hat, the theorem 1. And how to prove this one? So we want to minimize the sum of squared errors. And this is in matrix form, epsilon prime, epsilon transpose epsilon. Because epsilon transpose is epsilon 1, epsilon 2 up to epsilon n as row vector, and epsilon is this column vector. So actually the product is epsilon 1 square plus epsilon 2 square and so on. So then epsilon is equal to y minus x beta. So actually this sum of squared residuals is written as this way. Then we have to minimize with respect to A and B. So to minimize, basically, okay, so we have some function, and minimize. So then suppose, okay, so this is A, and this is the entire function, L of beta, and the minimizer A hat, at minimizer A hat, the derivative of this function LB. So basically L of beta, we differentiate with respect to A. This should be 0 because this is minimum. Okay, so this slope should be 0. So generally, so this should be 0. So that means this A and this B. So these are both 0 at minimizer A hat, B hat, pair of A hat and B hat. So that means that we differentiate this one. Differentiate this one, then this becomes this. Yes, actually we need the product rule. So we have two factors, the one factor and the two factors. And I think that and each vector is n by 1. This is 1 by n. Yeah, and actually we can derive that if we differentiate the yellow term, then this becomes X transpose. So this becomes X transpose times Y minus X beta, yeah. And actually when the second factor, the orange one, is differentiated, actually you can figure out that this again becomes the same one. So X transpose times y minus X beta. Just if we ignore the fact that these are vectors and matrices, simply, y minus X beta, if everything is scalar, the derivative is with respect to beta is negative X, right? So sorry, we need the negative sign here, but this becomes the negative of X, the 2 times X, as X transpose times y minus X beta hat, and this should be 0. But the negative sign doesn't really matter because if we have to equate to 0, then we can just multiply. We can multiply by -1 and multiply by 1/2. Then the remaining term, we can see that the X prime y minus X prime X beta hat is equal to 0. So that means the beta hat is equal to, at first we move this term X transpose X beta hat to the other side, then so you can see that this is the X transpose X and the X transpose Y. Then we multiply X transpose X inverse on both sides from the left, then we can get this. So we can prove this. So this proof is simpler, and actually it's more general than original theorem 1, because it can be extended to multiple linear regression. So matrix representation can give the solutions. So this is the case. And we can define why this is a predictor and this is X. So the predictor matrix, and the predictor matrix have the column of 1. So we have to include the intercept. So we have to combine these intercept column and the X column. Then using this Y and X, X transpose X inverse times transposed X and Y. Then we can get this answer. And this is the same as before. So in this way, we can calculate it. And the residual notation, so we calculated the residual, and in the matrix form, epsilon I hat is this way, and xi is, maybe I should say xi vector. So this is the pair of 1 and xi. And also in matrix form, all observations, all residuals, epsilon 1 hat to epsilon n hat is calculated by this way. So X is a n by 2 matrix, and this is 2 by 1, and this is n by 1. So you can say this is n by 1. Any questions? I think it's already 7:45. So